Imagine trying to solve a puzzle where the pieces are numbers, and the goal is to find the missing exponent. Logarithms are like the secret keys that unlock these puzzles. They help us answer questions like, what power do we need to raise a certain number to in order to get another number? Think of a simple example. 2 raised to what power equals 8? The answer is 3, because 2 times 2 times 2 equals 8. In logarithmic terms, we would say the logarithm of 8 to the base 2 is 3. This is written as log base 2 of 8 equals 3. Logarithms provide a different way of looking at exponential relationships. They offer a powerful tool to simplify complex calculations and solve problems that would be otherwise very difficult. In the world of logarithms, there are 2 types we encounter most often: common logarithms and natural logarithms. These logarithms differ based on the base they use. The common logarithm, written as log without a specific base, uses base 10. For instance, log of 100 equals 2, because 10 raised to the power of 2 equals 100. We encounter common logarithms in everyday scenarios like measuring the pH of substances or the intensity of earthquakes on the Richter scale. Natural logarithms, denoted by ln, employ the mathematical constant e as their base, which is approximately 2.718. This might seem like a strange choice, but e possesses unique properties that make it incredibly useful in fields like calculus and finance. Natural logarithms find applications in calculating compound interest or modeling exponential growth and decay. Just as we have rules for arithmetic, logarithms have their own set of rules that make them incredibly powerful for simplifying expressions and solving equations. The product rule tells us that the logarithm of a product is equal to the sum of the logarithms of the individual factors. For example, log of a times b equals log of a plus log of b. This rule proves particularly useful when dealing with large numbers or complex expressions. The quotient rule states that the logarithm of a quotient is equal to the difference of the logarithms of the numerator and denominator. In other words, log of a divided by b equals log of a minus log of b. This rule comes in handy when we need to simplify ratios or fractions involving logarithms. Lastly, the power rule allows us to bring down an exponent within a logarithm and multiply it. So log of a to the power of n equals n times log of a. This rule proves invaluable when dealing with exponents within logarithmic expressions. The logarithmic function and the exponential function are like 2 sides of the same coin. They are inverses of each other. This inverse relationship gives us a powerful tool for understanding and manipulating exponential growth and decay. If we graph the exponential function y equals a to the power of x, we get a curve that rises or falls rapidly depending on the value of a. The logarithmic function, y equals log base a of x, gives us the mirror image of this curve across the line y equals x. This inverse relationship means that if we know the value of an exponential function at a certain point, we can use the logarithmic function to find the exponent. And vice versa, if we know the exponent, we can use the exponential function to find the value of the function. Section 5. Expanding our horizons. Expanding and condensing logarithms. Mastering logarithms involves not only understanding their basic rules, but also knowing how to manipulate them effectively. This includes expanding and condensing logarithmic expressions. Expanding a logarithm means breaking it down into a sum or difference of simpler logarithms. We can achieve this by using the product, quotient, and power rules in reverse. For example, we can expand log of a squared b over c as 2 log of a plus log of b minus log of c. Condensing logarithms involves the opposite process, combining a sum or difference of logarithms into a single logarithm. This process proves useful for simplifying expressions and solving logarithmic equations. For instance, we can condense 2 log of a plus log of b minus log of c back into log of a squared b over c. Section 6. Logarithms in action, real-world applications. While logarithms might seem abstract at first, they play a crucial role in various scientific, technological, and everyday applications. In computer science, logarithms form the backbone of algorithms used for searching and sorting data. Their ability to handle vast ranges of numbers makes them invaluable in fields like data analysis and machine learning. In finance, logarithms help us understand compound interest and calculate the time it takes for investments to grow or decay exponentially. They are essential tools for investors, financial analysts, and anyone dealing with the complexities of the market. Logarithms are even used in music. The musical scale we use today is based on logarithmic principles. The frequencies of notes are spaced logarithmically, creating the intervals and harmonies we enjoy. Section 7. Sound, earthquakes, and stars. Logarithmic scales in action. To grasp the significance of logarithms in measuring the world around us, we need to understand the concept of logarithmic scales. These scales prove invaluable when dealing with quantities that vary over a vast range, making it difficult to represent them on a linear scale. One familiar example is the Richter scale, which measures the magnitude of earthquakes. This scale is logarithmic, meaning that each whole number increase on the scale represents a 10-fold increase in the amplitude of the seismic waves. A magnitude 6 earthquake is 10 times more powerful than a magnitude 5 earthquake, and 100 times more powerful than a magnitude 4 earthquake. Another example is the decibel scale, used to measure the intensity of sound. Like the Richter scale, the decibel scale is logarithmic, with each 10 dB increase representing a 10-fold increase in sound intensity. Even astronomers use a logarithmic scale, called the apparent magnitude scale, to measure the brightness of stars. This scale dates back to ancient times and reflects the fact that our eyes perceive brightness logarithmically. Section 8. Taming complexity. Logarithms as mathematical shortcuts. One of the most remarkable features of logarithms is their ability to transform complex calculations into simpler ones. This power stems from their ability to convert multiplication into addition and division into subtraction. Before the advent of calculators and computers, scientists and engineers relied heavily on logarithmic tables to simplify complex calculations. These tables provided pre-calculated logarithms of numbers, allowing them to perform multiplication and division by simply adding or subtracting the corresponding logarithms. While calculators and computers have made logarithmic tables obsolete for most practical purposes, the underlying principles still hold true. Logarithms allow us to break down complex problems into smaller, more manageable parts. This ability to simplify complexity makes them invaluable tools in various fields, from engineering and physics to finance and computer science. Section 9. Beyond the horizon, the enduring impact of logarithms. Logarithms, often seen as abstract mathematical concepts confined to textbooks, have played a pivotal role in shaping our understanding of the world and advancing various fields. Their ability to simplify complex calculations, represent vast ranges of data, and provide insights into exponential phenomena makes them indispensable tools for scientists, engineers, and anyone seeking to unravel the mysteries of the universe. From measuring the magnitude of earthquakes to understanding the growth of investments, from designing algorithms to composing music, logarithms continue to shape our world in profound ways. As we delve deeper into the digital age, with its ever-increasing amounts of data and complex systems, the importance of logarithms will only continue to grow. By embracing the power of logarithms, we unlock a world of possibilities, enabling us to tackle complex challenges and make sense of the vast and intricate tapestry of the cosmos.